Now, let's apply voltage between the two ends of the nichrome wire. And then we measure the voltage there with a voltmeter and the electric current with an ammeter. The voltmeter is connected to the 15-volt range. The ammeter at the 500 milliampere range. Both the voltmeter and the ammeter are designed for direct current. This nichrome wire has a resistance of 50 ohms. This is the power source where the voltage is applied. You turn the knob at the power source to apply voltage. The voltage is just now 0.5 volts. And the current is 10 milliamperes. The vertical axis of this graph represents milliamperes, and the horizontal axis, voltage. We'll now record the test figures on this graph. The voltage is now 0.5 volts, and the current 10 milliamperes. Now we further increase the voltage. The voltage has now been increased to 1 volt. This voltmeter is used for a 15-volt range. The current indicates 20 milliamperes now. So we put that on the graph, 1 volt and 20 milliamperes. This time we'll increase the voltage by 0.5 volts every time. Finally, we increase it to 4 volts, and the current shows the figure for 80 milliamperes. Now, you'll write the numerical values of the current, each corresponding to the respective figures of voltage on the graph by putting dots like this. These dots should be on a straight line. That means the voltage-current relations are in direct proportion to each other, or the current is in direct proportion to the voltage. Now let's remove this 50 ohm nichrome wire. And replace it with a longer one having the same thickness. The wire is connected like this. For a resistance of 100 ohms. We then increase the voltage as we did before. The voltage is 0.5 volts now. And the current in the wire is 5 milliamperes. Now, are you ready? 0.5 volts and 5 milliamperes. Now, let's increase the voltage to 1 volt. The current is 10 milliamperes. So, will you mark that again? 1 volt and 10 milliamperes. We'll now gradually increase the voltage by 0.5 volts every time. We continue to increase it up to 4 volts. And the current comes up to 40 milliamperes. Let's mark the graph again. 4 volts and 40 milliamperes. Each should be put to form a straight line. Now, we'll clarify the current voltage relation at 100 ohm resistance. The dots appear on the straight line, as in the case of the 50 ohm resistance. So, at 100 ohm resistance, the current is in direct proportion to the voltage. As the voltage is increased by 2, 3, 4 times, the current is also increased by 2, 3, 4 times accordingly. So the greater resistance interrupts the current flow so much more. Let's open this power supply unit. Here we see two of the 3-volt batteries connected in series. It's possible to change the voltage value by moving this sliding resistor. Now we'll have a test by using a miniature bulb as a resistor. We then turn the knob to increase the voltage and see the numerical values of voltage and current. When the voltage is 0.5 volts, the current is 70 milliamperes. So you'll mark for 0.5 volts on the horizontal axis and 70 milliamperes on the vertical axis. The voltage is now raised to 1 volt. The miniature bulb lights up. This bulb is used for 12 volts. The current, 100 milliamperes. And 100 milliamperes at 1 volt. Now the voltage is 1.5 volts. And the current is 125 milliamperes. So you put marks again. The voltage 1.5 volts and the current 125 milliamperes. In this way, voltage is gradually raised by 0.5 volts at each time to study the increasing intensity of current in the wire. When the voltage is increased to 4 volts, a little 12 volts bulb lights up as bright as this. The ammeter indicates the 220 milliampere level. So you'll put a dot to indicate 4 volts. And 220 milliamperes. Now watch. The dots do not form a straight line, do they? So let's now follow the dots to find out what they mean. Well, it looks like a mild curve, doesn't it? Well, if that's the case, we cannot say that current is in proportion to voltage. When the filament of the miniature bulb is lit, the current in the wire will not remain proportional to the voltage. This time we'll observe continuous changes in the current and the miniature bulb as they occur in response to those of the voltage. But it seems to have something to do with the filament of the miniature bulb being heated, and we'll see that in the next test. This is a coiled 1 meter long steel wire. Now let's charge the wire with electricity. This time, the ammeter range is 5 amperes. The ammeter indicator points to 1.7 amperes. We then heat the wire with the flame of an alcohol lamp. You see, the current is getting smaller and smaller. It has now come down to 0.5 amperes. So, as the temperature of the wire rises, the current becomes smaller and smaller. Now, we move the wire off the flame. And the current becomes gradually greater. Now we heat the wire once again. And the current becomes smaller. As you have seen, the current in the wire decreases when the wire temperature rises. This means that the temperature rise makes the current flow difficult. So the rule is this: the higher the temperature, the smaller the current. That means that resistance becomes greater. This figure contains liquid nitrogen. Now, what do you think has happened to the rose? Well, it's completely frozen. The temperature of the liquid nitrogen is as low as minus 193 degrees centigrade. Now then, what will happen to the current if we put the steel wire into this extremely low temperature liquid nitrogen? Well, what do you think will take place? Here we go. Oh, look, the indicator points to 2.7 amperes. The current, which should be 1.5 to 1.6 amperes in normal temperatures, has increased to as high as this. Now we lift it from the beaker, so the temperature rises, and then the current decreases like this. And here we again put it back to the low temperature liquid and get a flow of current in greater volume back again. You have just seen the fact that the current increases when temperature is lowered to an extreme degree, resulting in a much decreased resistance. So one of the resistance characteristics is that resistance increases or decreases depending on the temperature applied.